we can determine the electric field from the electric potential using calculus. You can see that for a uniform field, the electric field is just the change in potential over the distance between the 2 points. That's where the field is uniform, and delta D is just the distance between the 2 plates. This comes from delta V equals negative ed. But if the field is not uniform, we can simply reduce this relationship to its infinitesimal version. And very similar to the fact that the force in the x direction is the partial derivative of the potential energy function, negativized, can't forget that negative, the field in the x direction is the negative of the partial derivative of the potential function. So the field in the x direction is negative round v round x, the field in the y direction is negative round v round y, and the field in the z direction is negative round v round z. And as you will see, that's just analogous to the fact that the force is negative round u round x, force y direction is negative round u round y, and force z direction negative round u round z. That's just totally analogous. So let's take this example of finding the field from the potential function. So what we have is potential in terms of x, y, and z is negative 2xy plus 5xz plus 4yz. And we want to find the electric field in the x, y, and z directions at the given point. So to find the field in the x direction, that will just be the negative partial derivative of v with respect to x. And so that's going to be negative, I'm going to put the whole thing in parentheses here and negativize the whole thing. Well, remember to take the partial derivative, we just take the derivative with respect to x, but we pretend that y and z are just constants. If that is the case, then this will be negative 2y is our derivative. Negative 2y right there. Plus, take the derivative of this with respect to x, and then just pretend that z and 5 are constants, and then you get plus 5z. And then with this last term here, oh, there's no x. Derivative of a constant, those are all constants, is just 0. So that gives us positive 2y minus 5z. To find the magnitude, I just plug in these numbers right here. This will be 2 times 3. Again, all I'm doing is plugging in these numbers there. 2 times 3 minus 5 times z is 5 times 2. That gives me 6 minus 10 is negative 4 newtons per coulomb in the x direction. Let's do the same thing for the field in the y direction. We're going to take the negative partial derivative of v with respect to y. These aren't 2's, although they look kind of like that. These are rounded d's or round d's, so that's the partial derivative symbol. And that'll be negative of, in this term, in terms of y, gives us negative 2x. Plus, what is the derivative of this with respect to y? Well, it's just a constant, that's 0. And then plus this with respect to y will just give us 4z. And we plug in our 1, 3, 2 point, it gives us, I'm going to rewrite this one more time, 2x minus 4z. And that gives us 2 times 1 and minus 4 times 2. That is 2 minus negative 8 is negative 6 newtons per coulomb. Cool. And finally, the field in the z direction is just negative round v round z, which will be negative, and in parentheses I've got negative derivative of z of this one, there's nothing there, it's just a constant, just 0, plus 5x is the derivative there, plus 4y. So that gives us negative 5x minus 4y. And we finally get, plugging in this value of 1, 3, and 2, we get negative 5 times 1 minus 4 times 3. And that gives us negative 5 minus 12 is negative 17 newtons per coulomb. And that is our field in all 3 directions.